functions. And all that simply represents is an ability for us to then determine what is the instantaneous rate of change at a specific point on the graph. Because we know that, again, when we were looking at y equals x squared, it does not have a uniform rate of change throughout like a line does. So if I want to know how quickly, if I'm at, say, x equals 3, how fast is the graph changing? At what speed? So I want the slope of a line that is tangent at that point. How quickly is it changing? Depending on where you are on the graph determines your slope. Notice at different points the slopes, sometimes they're negative, and it looks like it for a while it gets less negative, and then it looks like it should get to 0 down here, and then it gets more and more positive. So depending on where you are determines how quickly you are moving at that given point. So how can I represent an ability to find any instantaneous rate of change? Well, that's going back to using our definition of a derivative. So let's do a simple one to start. So we're going to look at f of x is equal to negative 5x squared. The question is, how do I find an instantaneous rate of change at any given point on this graph? I know graphically that negative 5x squared is a parabola that opens down and is very skinny. Okay, so again, it does not have a uniform rate of change at any given point. So we have to look at a secant line that we merged onto making a tangent line. So I'm going to use that definition then, the idea of a slope, and we want the distance between the 2 points of that slope formula to become 0. So we're going to use the slope formula that we did in the other video. So we've got f of x plus delta x minus f of x over delta x plus delta x minus x. So that's this being delta x. Alright, so algebraically we can plug stuff in now. This represents our slope. Here's our y2, y1, x2, x1, right? We have our 2 points and we want the 2 points to merge to each other to get an instantaneous rate of change. Alright, so I'm going to keep my limit notation and I'm going to plug in our values, our function. So x plus delta x is going to go into our function f, our function f being negative 5x squared. So I've got negative 5 x plus delta x quantity squared minus f of x. Over delta x. Now if I were to plug in 0 using our ideas from the last bit that we've been working on, if I plug in 0, I get 0 over 0. So something must cancel, so we need to algebraically manipulate this. Alright, so if I start multiplying this stuff out, I've got negative 5 times x plus delta x squared is going to give me x squared plus 2x delta x plus delta x squared, that's the first part, plus 5x squared in this case. And I'm just going to keep going algebraically down. So I'm going to carry that negative 5 through. So I've got negative 5x squared minus 10x delta x minus 5 delta x squared plus 5x squared all over delta x. So now I see that this cancels with this, and I notice that everything that is left here has a delta x at least 1 in common. So I'm going to pull out a delta x. And that's going to give me negative 10x minus 5 delta x over delta x. So now my delta x cancels in the top and the bottom, and I'm left with negative 10x minus 5 delta x over 1. Okay, so now I can plug in delta x equals 0. So delta x equals 0 is this piece right here. So I have negative 10x minus 5 times 0. So I have negative 10x minus 0. So that means my derivative is negative 10x. So what this allows me to do now is if I want to have a specific point, an instantaneous rate of change, how fast am I moving at x equals 1? I would plug in x equals 1 and it would tell me how fast I'm moving at that point. Let's look at a couple more. Let's look at the function f of x is equal to the square root of x. So again, square root of x, if I think about this pictorially, I get something that looks like this. Okay, so if I wanted to know how quickly this graph is changing, say at this point right here, I can't do it with one point. I need rate of change, a slope of the tangent line. So I'm going to have to pick another point on this graph, draw the secant line between them, and then picture this yellow line, or this yellow point, merging down to become the orange line. Okay, so that means the slope between these 2 points, and I want the distance between them, that change in x, to become 0. So f prime then is going to be looking at the distance in the x values to go to 0, and then we do our slope between the 2 points. So that's f of whatever x plus delta x is minus f of x, and then it simplifies down to delta x. So plugging in our formula, oops, forgot my limit. We have the square root of x plus delta x minus the square root of x all over delta x. y2 minus y1 over, and then the x2 minus x1 is simplified down to delta x. So again, if I plug in 0 for delta x, in here and in here, I do in fact get 0 over 0. I would be left with the square root of x minus square root of x, which is 0 over 0. So algebraically, something must cancel. Okay, so back we used the conjugate, top and bottom. All right, so if I do that, I'm left with x plus delta x minus x over delta x times all that stuff. So this simplifies down. X plus delta x minus x simplifies down to just delta x in the top, and I'm not going to multiply any of that stuff through. Okay, so those cancel. So I'm left with 1 in the top and square root of x plus delta x plus square root of x in the bottom. Now if I plug in 0 for delta x, I have 1 over, I'm going to have x plus 0, so square root of x plus 0, which is square root of x, plus square root of x. This simplifies down to 1 over 2 square root of x for our derivative. Again, this represents a function to represent all slopes. So if I wanted a specific instantaneous slope, I'd have to plug in an x value to get a numerical answer out. The next one in your notes is 1 over x. I'd like you to try that one for yourself for next class. That one's going to end up with fractions where you have to find common denominators and all that good stuff. So now, after you do that one, let's look at sine of x. Actually, instead of y, let's go ahead and make it an f of x. All right, so again, let's find the derivative of sine of x. So I'm going to just jump right to the limit notation. This one gets a little more hairy because we're dealing with trig, which means we're going to probably use our identities. So I've got sine f of x plus delta x minus f of x all over delta x, and we're looking as delta x goes to 0. So if I plug in 0 right away, I get sine of x minus sine of x over 0, which is 0 over 0. So the tough one with this is remembering the identity for sine of x plus delta x. This is a sum property. So if I go back and look at all of my different identities from pre-calculus, the sum property for sine is sine of x cosine delta x plus cosine x sine delta x, and then we got minus sine of x all over delta x. Now you're probably wondering, well, what the heck does that do for me? So what? But I see two pieces that have a sine of x. I see this one has a sine of x, and I see this one has sine of x. So I'm going to kind of reorder the way this is written. And I'm going to make this cosine of x sine of delta x plus sine x cosine delta x minus sine of x. And I'm going to think of this as two separate entities. I'm going to, because I have this plus sign stuff going on in here, I'm going to kind of picture doing the limit of this piece and then adding to that the limit of this stuff together. Alright, so what does that look like? Alright, so if I do cosine of x and then I have sine of delta x over delta x plus, I'm going to go ahead and factor out the sine of x. So that leaves me with cosine of delta x minus 1 over delta x. Okay, so I am thinking of doing these two pieces separately. So what this does for me is I see our special limits that we learned before. I see a special limit here. And I also see a special limit here. This one going to 1, this one going to 0. So now I have the limit of cosine of x times 1 and sine of x times 0. So this whole piece becomes 0. So now I'm just doing the limit as delta x goes to 0 of cosine of x. Well, as x and times 1. There is no delta x in this particular equation, so I just am left with cosine of x. So f prime is cosine. The derivative of sine is cosine. Again, in order to find an exact instantaneous rate of change then, I have to plug in a specific x value. So I would like you then to try both f of x equals cosine and the last one, f of x equals e to the x. Remembering e to the x, that one's going to be your challenging one, and remembering our special limits.